Okay, hello everyone. Thank you for joining us today. So we're just about 1 minute past the hour. So welcome to the ENLA seminar. I'm Alex Townsend from Cornell University, and I'm the host for today. I just want to quickly remind you of the protocol. So if you would like to ask a question during the talk, we encourage you to do so. If you're watching us on Zoom, then you can do that with the Q&A window at the bottom. That's monitored by Valeria. If you're watching on YouTube, you can type a question into the live chat window, and that's monitored by Bart. So today we're very excited to have Sherry Lee joining us. Sherry is a senior scientist in the Computational Research Division at the Lawrence Berkeley National Laboratory, where she heads up the scalable solvers group there. She works in high performance scientific computing, so like parallel computing, sparse matrix computations, and high precision arithmetic. She also has impressively turned her computing expertise to help domain scientists in large scale applications, such as chemical engineering, earth sciences, and material science. She earned a PhD in computer science at the UC Berkeley. She is a SciAm Fellow and an ACM Senior Member. So it's an absolute honor to have her join us today. So Sherry, the Zoom stage is all yours for your talk, Auto-Tuning Exascale Applications with Gaussian Process Regression. Thank you.
Thank you, Alex, for the kind introduction. And also, I'd like to thank the organizers for inviting me to give us this opportunity to talk about this work. And this work is actually fairly recent. We started about 3 years ago. This is when the US exascale computing project started. We got this joint funding between UC Berkeley and Lawrence Berkeley Lab. And then after this couple of years, we spent quite some time exploring different options of what to do to finish this task. And it turns out it's a lot of elements involved. So it's still very much a work in progress. So I'd like first to introduce the team, and I guess virtually introduce the team. And we have several staff members at Berkeley, and like Jim Yang Liu and Osni Marquez. And also we recently, the two postdocs joined us a couple of months ago. So it's good to get some new manpower to work on this. And in the past, we are very fortunate to have several people working with us. Wissam was a postdoc started 3 years ago, and right now he's with the Jack Dungara's group with the University of Tennessee. So he built a lot of fundamental infrastructure, the baseline infrastructure of the software. And Mosen is a PhD student with Tim Davis. Changmeng is a PhD student with Jim Nagy. Xinran is a PhD student with David Bindel. And these are summer students. And one of the things I'd like to mention is like Changmeng is getting this NSF fellowship from the Mathematical Science Division. And the fellowship is to get people to work at the national lab. So in the past, we have sponsored like 6 or 7 these fellowship summer students. So if you are in US university, consider getting your students to join this program. They started about 3 years ago. Okay, so the problem we're dealing with is you have a certain problem, like a simulation problem or solving a linear algebra problem, and you have a code. This code has a lot of parameters to solve this problem. And you want to find the parameter configuration, which can be the combination of several values to optimize, improve the code performance. And the metrics could be a lot of things. So the common ones is solution time, memory, or energy use, and could be the combination of a couple of parameters. And one of the characteristics of the ECP applications, they are very costly. First of all, they run on large supercomputers. And secondly, they can run very long time, sometimes weeks. And the goal of our work is to make best use of the limited number of runs. So you cannot afford to have too many application runs. So I'll start with one motivating example. This is the parallel dense QR factorization in scalable. I think a lot of people are familiar with this. And on the upper right corner here, I have a small 5x5 matrix. I divide into 2x2 block. So now I have 3 blocks. And then I have 4 processes. It's mapped using 2D block cyclic layout. So 0, 1, 2, 3, okay. And my task is try to optimize the parameters NB and the processor configuration so that I solve particular problem as fast as possible. So on the picture here, I show 2 pictures. The top picture is we do, let's say, semi-exhaustive search of the parameter space NB. So x-axis is NB, y-axis is NB. And this is run on 24 cores of Cori machine at NERSC. And this particular task is 2000 dimension. And then you can see that this vertical axis is the runtime. There's we do the different number of processes. So probably 2, 6, 16 or something up to 32, up to 24 in this case. And then you can see that if you run on one node, you can clearly see the with different number of processes, the runtime it's pretty much very much divided as expected. You can see the clear layer. But when you increase the number of processes, the machine size, then a lot of noise happens here. So this one we run on 300 cores. So then there's no clear cut about your objective function value. And that's a very non-smooth. It's a difficult problem. And then what is the best parameter configuration in this case? After a lot of search, we found that for problem 2000, the NB, the block size is 48. The process configuration is 2x12. And the time is this. And for 1000, NB is 126, and process configuration is 16192. So you can see that even for this relatively simple problem, the best configuration is not something you will customarily think. So conventional wisdom for scalable, if you look at the manual, is we try to give block size as square as possible and also process configuration as square as possible. But the best value is actually not a square. So that's a little bit surprise. Okay, so I'll just summarize the optimization problems we're dealing with. So there's no analytical formulation of anything like objective function, the gradient, there's no gradient. The problem constraints also, very often there's no explicit formula. And then in the optimization, we talk a lot about function evaluation. So in this case, it's considered expensive application runs. It can be, each run can be up to weeks. And then I show you there's large variability related to hardware mostly. So it could be network, could be the disk I/O. And this problem is getting worse when you increase the number of nodes. And certainly it's not convex. And also about the parameter space. So we can have real parameters, integer parameters, and sometimes it's categorical. So then all these characteristics, if you are an optimizer, it's the headaches for any optimizer, basically. Okay, so after some research, we decided to use a Bayesian optimization framework. And it's a statistical inference. The workflow is an iterative model-based approach. The reason we choose this is because it's very versatile. So it doesn't matter what your function is. It's black box, treat function as black box. And also it's a derivative free. So it's a global optimization approach. And this workflow here, the chart shows basically the different elements of the algorithm. So for example, you can start with doing several evaluations, sample several locations of the parameters, and then build a prior distribution. And very often the prior you put a prior distribution on these initial samples. For example, could be the normal distribution, like with the mean and the covariance. And let's say, suppose you know the function very well, and then of course we don't. But if you know, let's say we know that, then you actually can get the initial samples at a good, perfect location. Then you build this surrogate model, and that will reflect very close to your objective, and then you're done. So that's the ideal situation. But certainly nothing is ideal. So then what we need to do is this iterative process, this cycle, to keep updating this surrogate model. The purpose of using this surrogate model is that's a lot cheaper to evaluate compared to the original function. And then it's probably has a very good prediction of your function surface. So the goal here is fx approximately y, and then we want to minimize this. So this cycle is basically you, based on, for example, initial samples, build a first surrogate model, and you search for the next point to do the function evaluation. Then you optimize a certain acquisition function to improve, then update this model, update the posterior distribution based on the Bayes rule. So that's the cycle. And then what we do, so each of these box modeling and search, there are a lot of different methodologies. So what I will talk about is what we do here. So this for this box, we use GP regression, Gaussian process regression. And then we extend that to multitask learning, LCM model here, which I will talk about. And then for the acquisition function, there are also a lot of options. So here we are using expected improvement, and we maximize this EI, use the, for example, what is this? Particle swamp optimization and those global optimization techniques. So I'll dive into these two components. Okay, the first part is about modeling. So this picture shows the QR factorization at different tasks. So you have different dimensions. And then with the modeling, hopefully you can recover this surface with either with multiple tasks or single task. So that's the goal here. And you can have many tasks. And the thing is, if you have a multiple task, multiple size you want in your application you need to do, you can use them to help you to build this surface in a cheaper way. That's the general idea. So the single task modeling use this Gaussian process regression. A good reference is this book. And then this can be extended to vector valued functions. And the model is called LCM. And that's a very good paper about this vector valued. Okay, so Gaussian process, it defines a distribution over functions, and then your inference takes place in the space of functions. Essentially, it says, suppose you have evaluated a number of function points, and then if you look at any finite set of variables, this will follow the multivariate normal distribution. And it's specified by the mean function and covariance function. usually it's called a kernel. It's the correlation of the function values. So the notation here is this model will follow the GP with the mean function and the covariance. So mean is this expected value of model function, and the covariance between 2 points is given by this. So that's standard notation. And we use, currently we use Gaussian kernel, which is one of the most popular kernels. So it's given by this exponential square negative here. So essentially, if this D is the number of parameters in your code. So it's the high dimensional feature space. And covariance will be large if 2 points are close together. So that's how we try to, so if you have a smooth surface with this modeling, then you can get this surrogate surface, response surface very nicely. And then the one of the ingredients here is the model prediction. So after you build with the existing data, you build the model. So given, say, the S observation pairs, the parameter configuration, the function value here, and you add a new point, X star, then you want to update the posterior probability distribution, which is given by this, it's also a normal with the new mean function and then the new variance. So this prediction of the model mean and the variance corresponding to the confidence, you can write out the exact formula, which is the mean is the original mean and updated by this quantity. And the variance is the prior variance and subtracted this quantity, meaning that after you add new data, your variance will become smaller. So which means your confidence, it will be increased. So that's intuitively, you can explain this mathematical formula. And this is a simple function, f of x equals to x times sine x. And in this picture, there are 6 observations. There are these 6 red dots, okay. And then these 6 red dots are the observations. And using this Gaussian model, you can predict the blue curve here. And the actual curve is actually, actual function curve is this dotted one. So then you can see that within for each prediction, there's a 95 confidence interval. If you put down that interval, plot that, so this is the 95 confidence interval of your prediction. So this part of the prediction is very good, and this part is less good. So now that's the basic idea about a Gaussian model, which is for single task. If you want to optimize, you just keep looping around that, the workflow. So now we're extending this to vector valued functions. So we call this multitask learning autotuning, MLA. And here you consider a set of correlated objective functions. So for example, if you want to do the QR instead of one problem size, and you probably want to have a 10 problem size you need to deal with. And then the question here is that this delta is 10. And whether you can use this multiple function evaluations to help you to build the GP models, which is cheaper to build and also as accurate enough as if you do each task one at a time. And the particular model we're using here is called the linear co-regionalization model, LCM. So it attempts to build a joint model of the target functions through the underlying assumption of linear dependence on latent functions. So you have underneath, there's several latent functions. Each of these latent functions we also model using a single GP. And this combination, this linear combination of these latent functions, it should describe the shared behavior of these multiple tasks. So that's this, each of these Fi is a linear combination of this. And this Q how many do you want to use? It's usually small is good enough for several, but it's you never use that more than the number of tasks you are considering. And then for each of these latent function, we also have the kernel function, the correlation to describe this, and then with each of the individual, the hyperparameters here. So for this vector function, the value, the LCM model is pretty straightforward extension of the Gaussian process. So the model prediction here is you have delta tasks, right? Then you group them into S observations of each task. So this is one group of tasks with S samples and another group of tasks with S samples. And each of the pair them have the function value evaluation. And for one point, there's a new point coming in here. And this is a set of new configurations corresponding to the different task, okay? And then you update the posterior probability distribution, which is given again by this normal distribution with the new mean and new variance. And the mean update is the same. You update based on this big covariance function, and then the confidence is improved by this quantity. So the difference between this single and single GP and this LCM is really your covariance matrix becomes big, which includes both autocovariance and cross covariance, which across the multiple tasks. So the covariance matrix is given by this the sum of all the covariance between the tasks and also within the task of all the samples. And this is the regularization term. Okay, so in the modeling phase, one thing I just want to mention quickly is as you can see, there are a lot of hyperparameters. All these red are hyperparameters. And you need to learn this also through some optimization. And luckily, this you can actually write down this with gradient. This is available. So that's the stage to maximize the marginal likelihood. It's equivalent to minimize the log likelihood, minimize this quantity. And gradient is available, so you can use your favorite gradient-based optimization. In our case, we're using this variant of BFGS. And then we parallelized this algorithm with several levels of parallelization. In particular, the expensive operation is this one, the covariance matrix inversion. We use a scalar pack Cholesky factorization. Okay, so that's the modeling phase. So the next phase is search phase. Suppose you already have a good model, and what do you do? Where do you place the new points? That's the big question we want to answer. And then given the new sample point, you want to quickly update the existing model. And the idea here is to find a point which could maximize something called the acquisition function. So this is another optimization problem, but easier. Although this problem doesn't have a gradient. The point you choose need to balance between the exploitation and exploration. So exploitation, meaning that you want to search the local area within the promising regions that you already explored, so that from your previous information. Exploration is to do some global search of new regions, which probably have more uncertainty, but the payoff may be better. So there's a balance between these two. And there are a lot of ways to define this acquisition function. And our current implementation is to use this expected improvement, EI, which is quite commonly used as an acquisition function. So the idea here is that suppose you propose a new point, xi star, and you look at the expected difference from the current best. This is your current best. And you can look at the expected difference of this current best. And then you want to, this formula you can derive actually by, if you look at John's paper, it involves a lot of chain rule, etc. You can derive explicit formula. So the expected improvement is this quantity, and this function is the ramp function. If the bracket plus is a ramp function, like in the neural network, the ReLU function, if you're familiar with that. So that just to say takes the max of this quantity and the 0. So if it's positive, it's this quantity. If it's 0, if it's negative, it's you take a 0. And then this the ramp function of this expected difference. Then the two function, one is the small phi is the probability density function. Another one is the cumulative distribution function. So as I said, this problem does not have a gradient. So we need to use some other black box optimization algorithm. So for example, the particle swamp algorithm we're using and some other options. But the time to do this, to optimize this is really fast. So let me circle back to my initial this workflow of the algorithm. And we can, so I explained all the fundamental elements in our infrastructure. So we can have a pause here in case people have questions, then I will move on to look at the results.
There are no questions on Zoom.
Also not on YouTube.
Okay, very good. Okay, so people are ready to go. So I plan to spend about 20 minutes to talk about the result. And as you can see, what I talked so far is mostly in literature. But when I talk about results, I will bring out some of the new features that we have implemented in our infrastructure. Okay, the first thing I want to mention is the software. Although this is not the focus of this talk, but it's by no means the small part of the project. We actually spend a lot of time to try to get this workable. So now you can download, you install, you can do optimization with your any function. And the software is a Python interface. So we leverage existing Python packages. In particular, this GPY has a lot of GP algorithm in there, and then some machine learning packages like scikit-learn, scikit-optimize. And also, since we're doing the MPI, large-scale parallel machine, so we use this MPI for Pi library. And the C code in our C code and actually Fortran code, we need to use is really the parallel matrix operations, like inverting, solving the systems involving the big kernel matrix. And from user point of view, it's actually not so much involved. So you will need to define the parameters, either categorical, integer, real, and the ranges of those values. And the involved process is to define the application as a black box function. So which means you will need to have a Python code, Python to your C Fortran interface. Usually the application code is in C or Fortran or C++, etc. So the only thing you need to do is to have this interface. And this is well-defined in programming language, so it's not a big problem. And if you go to the software, we have all the script, various script examples of doing, for example, Scalapack Eigensolver, doing the super LU hyper, etc. So essentially you can modify those scripts to fit your application. And optionally, you can define the constraints of the parameter space, define the performance models if you have one, and choose the search method. We have implemented different search method. So one of the challenges of developing this software is the parallelization aspects, because we want to, our tuner itself is parallelized across multiple nodes, and also the application can be run in any parallel mode, large scale machines, a mixture of MPI, OpenMP, or GPU CUDA programming. And one of the difficulties we encountered, actually, Wissam spent a lot of time, found a very good solution, is the different supercomputer, they have different way of launching the parallel job. And in the beginning, we just say, every time we do function evaluation, we'll submit the job. But it turns out, depending on the job scheduling of the system, the job could be waiting there for a long time. So that means your function evaluation time is actually counting, capture the time of the waiting time in the queue. And that's certainly not good. It's very bad. Your model will be built not on the function evaluation. So Wissam found a way to say using, MPI spawn facility, so that you only need to submit job once, and then your whole application tuner is running in the one big execution model without waiting. You wait in the queue once, but the whole process is no waiting time. So it's not a small task. I just want to mention. And I will give you examples of tuning on different math libraries and application code. And specifically, we are using the Cori machine at NERSC, which has the Intel Haswell node. And each node has 32 cores. So we use the up to 16 nodes. And as you can see, the problem here is going from simpler to more demanding. And these two codes are the full-blown fusion device simulation code. And the number of parameters also varies. The largest one we tried is the this multigrid solver, has 12 critical parameters we were tuning. Okay, so I will talk about several aspects using the examples, illustrating the various features, the new features we have implemented. The first, I want to mention the parallelization of the tuner itself. So there are two phases, the modeling and search. These are all parallelized. And to illustrate that, we use this demo function. It's a simple analytical function, so that function evaluation is cheap. Just evaluate this. And the reason to use that is so that you don't have function evaluation time to get in the way. And this is really the time I'm showing here is really the modeling and the search phase, the time. And the experiment here I'm doing is 20 tasks. So 20 from this T is the task. It's 0 to 9.5. And for each task, so we do 20 to 320 samples. So 20 tasks times 320 samples, your big LCM kernel matrix size will be the product of 320 times 20, so it's 64,000. So this is the linear algebra problem you want to solve the linear system with this covariance matrix, 6,000, okay? And 32 cores. So if you look at these function, the different t, with a smaller t, if t equals to 1, you get the shape is like that. With increasing t, it's very wiggly, so it's getting more and more difficult. So then we have 20 of those from 1 to 20. So you from easier to difficult, then you do the multitask learning together. So then this is the speed up of modeling. So from samples, initially you have 20 up to 320. Then you can see that the running time of, look at the black set of two curves. This is the search phase, 1 MPI. This is search phase of 32 MPI. And this is the modeling phase of 1 MPI, modeling of 32. So you see the benefit of parallelization. And then we look at the symmetric eigensolver in ScalaPack. Also, it's a parallel. So this particular algorithm is first to reduce the full dense matrix to tridiagonal problem. and then you run the bisection plus the inverse iteration to solve the tridiagonal problem. Then you back transform to get the eigenvectors of the original matrix. And for single task, we look at the dimension of this problem. This is the task. It's 7,000, and we give two different situations, two samples. One is 19, one is 180. And then for multiple tasks, we consider 9 tasks. So in addition to this 7,000, we add 8 more tasks, which ranges from 3,000 to 7,000. So these 8 additional tasks are relatively small, and we still want to find what's the optimal configuration for them. And in this case, compared to the single task setup, per sample, per task, you use 10 or 20 samples. So it matches this single task, the budget. And currently this experiment is on one node, 30 cores. So you can see that in this table, I gave you the different time. The total time for single task is 9,000 seconds, and multitask is cheaper. And objective function evaluation is here, then the modeling and the search time. So for this problem, the most of the time, majority of the time is spent in objective function evaluation. The modeling and search is relatively cheap. And it's because the reason is this number of parameters, only 3, I think. So your covariance matrix is relatively small. So the linear algebra part in the modeling search part is relatively trivial compared to the function evaluation. And then for this, you picture the same experiment. The picture basically shows when you increase the task. So I have 9 tasks here, and what the model find the best and the worst relative using all these samples. So the one point we can pay attention to is this one, the 7,000 case. With the single task optimization, this purple one gets the minimum and the max, best and worst. And if you use multitask, it's actually this yellow one. A yellow one is still single task. This red one, you actually get quite similar to the optimal using single one. But you get, in the multitask case, you get all of these 8 other tasks minimum also. Okay, so the next one is the fusion simulation codes. This one is also, we're trying to illustrate for big full-blown application and what is the characteristic of the tuner. So this code, these 2 codes, they solve the extended magneto-hydrodynamic equations. This is critical simulation code for building the reactor tokamaks. Right now, ITER is being built in France. And the linear algebra problem is actually dominate their simulation. So they have a linear system, and the linear solver is a GMRes, and using SuperLU as a block Jacobi preconditioner. It's a sparse linear system. And majority of the time, almost 80% of the time could be there. So the 2 codes, they have different characteristics. So one has, currently we tune only 5 parameters. The other one, we tune 7 parameters. And here this is a nonlinear iteration. So it's difficult to say what do you mean by multiple tasks. So what's our configuration here is we use the number of time steps in the nonlinear iteration as our task. So for example, for this code, the single task is we stop the simulation after 3 nonlinear steps. And then multitask is we choose 1, 1, 1, 3. So we stop, the first task is stop at 1, the second stop at 1, and the fourth one is stop as 3. So then with the single task, multitask, we get the minimum almost the same. And also for Nimrod, the single task, multitask, we got almost the same, the minimum. But then by use of multitasking, the total modeling time, this time, I would say, I'm not sure how much modeling time is probably small. But the total time, the function evaluation, you need less time. So you save a lot of time. And similarly, with multitask, you save a lot of time. So I have about 10 minutes I can finish. And the next one is the feature I want to illustrate is suppose you have a good performance model, which can be a very coarse model to predict performance. And this turns out can help the tuner a lot. So especially in the situations for real simulation, you don't have too many sample points. And this model is a good helper. So the algorithm here is what we developed is to add the model value. So this model value could be given by some closed formula as a new feature in the parameter space. So your parameter space is enlarged by maybe 1 or 2 more. The LCM matrix has the same size, but with enriched information. So your linear algebra part is modeling part, the cost is roughly the same, but you have more better information to guide you to build the model. And this example is coming from the demo function, which I showed you. So what we do, the model here is just contrived to just illustrate the purpose here. So we do some kind of scaling of the true function to use as a model. And this is the random perturbation here. And the example is we use t to 1 to 20 tasks. Remember the tasks, the function gets more and more wiggly with the higher task number. And the experiment we did has 20 samples, 40 samples, or 80. So it's different bars. So let's focus on the situation when the samples is small, because that's the situation we are most interested. And then you can see that with the increasing problem, the difficulty of the problem, this model actually could give you much more better performance. So this chart is the ratio of the tuned minimum without performance model over the tuned with performance model. So the higher, meaning that a model helps a lot. And the bottom part is the ratio of the true minimum versus the performance you get with model. So for the earlier task, you get the true, and with model, it's the same. It's only when you get very difficult task, your model, this tuner may not get the best, but those are very difficult functions. And similarly, this model can be used for example, for scalar pack, linear algebra, dense linear algebra, all of the performance model in dense linear algebra can be expressed by this formula. In fact, a lot of applications. So it's the number of the count of the flop and the time per flop and the count of messages and the time per message, the volume, how many bytes you transfer, then the time per byte you transfer. In this example, we do 5 random tasks. So you want to do the QR of mn, which is smaller than 20,000. 5, you choose 5 of them. And again, let's take a look at the example with smaller number of samples. So the blue bar. And it helps a lot if you, the sample, you don't have enough sample. But if you have a lot of samples, you can afford to do a lot of function evaluation. So the model may not be useful. It's since you already get a lot of information. So the next thing I want to illustrate is also a new feature we implemented is the multi-objective tuning. And it's best illustrated using the sparse direct solver. So as you know, sparse direct solvers are very memory demanding. So often time is not just the single thing you want to minimize. You also want to minimize the memory together. So it's practically very useful to minimize, consider them together. And in SuperLU, there are 6 parameters, the sparsity permutation, look ahead pipeline in parallelization, the process grid is also the similar like 2D block cyclic layout as a scalar pack. So it's total number of processes and what's the process row dimension, and then the block size. And in this picture, it's one of the matrices from the parsec group from sweet sparse that Tim Davis maintained, this matrix connection. So you can see that the tuner, when you use the multi-objective, the tuner will return the multiple parameter configurations, these black dots. Each of these configuration corresponds to a combination of the time and memory. So this gives you this plot. If you connect this black one together, it's called a Pareto, optimal Pareto front. So that means you cannot get some point here. You cannot get a parameter here which has a minimum time and memory. So the best you can do if you want a time minimum here, then in order to get a smaller time, the memory you have to use more memory. So this is the best you can do in terms of optimize both of them together. And the default value, this is the SuperLU. If you download the default parameter setting, is far from the optimal in both dimensions. And if you do the single parameter optimization, so for example, just optimize time, it's roughly here, it's very close to this Pareto front. And also if you only optimize the memory, it's here, so very close. And to implement this, the algorithm is with, let's say you have a gamma objectives. So the way is you build the modeling, the LCM model for each of these objective function. And the difference is the search phase. So we have to use this multi-objective evolutionary algorithm to find the k new points in each iteration. So this one is actually quite expensive. So if you want to do multi-objective optimization, you have to pay a lot. It actually can be much more expensive than the search in the single objective case. And so this is the multitask, multi-objective illustration. So we consider, in the sparse case, we consider parsec the family, the same family of matrices. They should have the similar characteristics. So that's how you can do the multitask learning and the two objectives. So it's each of these set curve is the Pareto front of the two objective function values. Okay, so I think that's the last experiment I want to illustrate is the HyperMultigrid Solver. It has 12 different parameters, which is the largest in our collection so far, in our experiment so far. And the tuning task is to solve the 3D Poisson equation or convection diffusion equation. And the task is to vary the problem size by the 3D problem discretization size and X and Y and Z. And the experiment here we do is 30 tasks are tuned together. So we use multitask learning. And we compare with the two popular tuners already you can download from these two sites. One is OpenTuner, one is HyperBenster. There's a lot of numbers to read, but don't spend too much time yet. What I want to illustrate is two points, basically. One is to compare GPTune versus these two tuners. And another one is to look at the tuner's stability metric we call the stable task. So the experiment here is you have a different kind of PDEs, okay, Poisson convection diffusion equation, and different number of processes. And the budget is the maximum number of function evaluations you are allowed to do. And then the first metric we want to look at is the win task, is the percentage of tasks where GPTune obtains better results than the other tuners. So there are two comparisons. One is compared to OpenTuner, one is compared to the HyperBenster. So for GPTune, one compared to OpenTuner, we have for across the board over 60%, 70% of the time, GPTune is doing better. And similarly, compared to hyperband, we have sometimes over 80% of the time we are doing better. So this is a very assuring result. And then another metric, which is actually very widely used when you compare different tuning results, because there's a lot of things. What do you look at? Is the independently to measure the each tuner performance, and then to see when you increase the number of samples, what is the, if you stop, for example, at certain time, and what is the best so far compared with what's the best of all time. So they call this anytime performance. And that's good because in expensive calculation, you probably don't have a budget to do 30 evaluation, 30 samples. So then you have to stop in the middle, and that will tell you whether your tuner is good in this metric. So then you can see, we say good, in our case here it's arbitrarily, we'll say if this ratio is smaller than 1.25, we'll say good. So with this metric, you can see that GPTune is good for a lot of the cases at any time. And then the other tuners, their percentage anytime good is less good as GPTune. So that's just a summary of the hyper results. And for win task GPTune, we wins on average 70%. So it's 21 out of 30 tasks, so we're better. And then for stable task, GPTune always shows the best anytime performance. Okay, so let me summarize. And we, as you know, said, we built all these on top of the general framework, this Bayesian optimization framework. But some new features we have implemented. One is particularly MLA. This helps the situation when the function evaluation is very expensive. And then we support multi-objective and also multi-fidelity, which I don't have time to talk about today. It's also the new feature we implemented. We use this multi-armed band optimization technique. And the user can input for performance models, and everything is parallelized on distributed memory machines. So the last slide is about the current and the future work. And the first thing right now we're actively developing is to get a history database to store the already evaluated functions. Since all the functions evaluated, they are quite costly, we want to keep the record. And in terms of content, we haven't quite settled. Certainly you want to record runtime, but machine specification, compiler specification, library versions, etc. These all needs to be saved in order for the results to be reproducible. And then we want this database to be accessible by the users, and also users can submit the data into this database. So that will involve some other issues like security issue. A lot of other issues are not mentioned. We haven't discussed in very detail. And another thing very important in large-scale computing is non-smooth surface. As my first example I showed, you can have very wiggly function when you have running on large-scale machines. So the different techniques we're looking at is to use different kernels to partition the space into piecewise smooth regions. So you do GP on each region and then additive together. And deep GP is combined with neural networks. And the last technique is a sparse GP. So for example, the simple case is a straightforward way is this kernel matrix. You can do off-diagonal low-rank approximation. And we have a software strong pack to do that. The next thing will incorporate that. And another thing is some techniques mentioned in a couple of lectures earlier by Elizabeth Ellman about the sparse GP. These techniques can be also used here. The most challenging problem, probably, in terms of accuracy of the model, is we haven't probably encountered is even higher dimensional problem. the number of parameters, for example, is bigger than 20, if you read the papers, they say that could be, bigger than 20 could be, quite difficult for this kind of optimization. So that remains to see. Okay, and thank you very much. And glad it's a little bit over time. I was targeting to finish in 15 minutes.
Okay, thank you very much. There are no questions on Zoom, but I do have a short question about precisely what you just said about the generalization to more than 20 parameters. Actually, the parameters people are interested in now is far more than 20. So what do you think could be to 2,000 or say many more than 20?
I don't expect these to go to 1,000. It is still, I think, in the order of tens, at least for the application code. A lot of them, for example, Hyper is a pretty sophisticated library, and it only has 12. And I'm not sure whether you have concrete example of, say, your application code that has 1,000 parameters. We certainly would like to see.
Well, it depends on the problem.
Depends on the problem, yeah.
Okay.
Yeah, we would like to see
I'm
those
done with Zoom. So Bart?
Yes, there's one question on YouTube of somebody with a cryptic name, so I don't know who asked it. And it's a fairly technical question. Suppose you have an objective function that's rather fast, let's say less than 100 milliseconds in a single thread, and you optimize for 50 parameters on a multi-core machine. Then how fast is the iteration? And then the second question is, does the iteration time increase if you start iterating the tuning function?
The first question, I expect that it depends on your, I expect it's pretty fast. But of course, it depends on your number of parameters. So that determines the matrix, the covariance matrix size, which we have to solve the linear system every step.
But saying around 50 parameters.
Oh, sorry, 50. Okay. So 50, and also depends on how many tasks you want to look at to optimize. So then you 50 times, say, the number of samples, it's 20, so 100, then you get probably several thousand matrix. And for that size, the modeling phase, search phase is fairly fast.
Okay, and does the iteration time increase when you have more iterations, like more than 500?
Yes, so every iteration you will need I think for all these applications, very often we need tens, in the order of tens iterations or something. Oh yeah, depending on the sample. So it's like 20, 30 iterations. So every iteration, your covariance matrix is increased by size. So each iteration, one after another, it's getting more and more expensive.
Okay, thanks. That's all for YouTube. Valeria or Alex?
Alex.
Cleve Moeller has his virtual hand up. So, Bart, are you able to unmute his mic?
Yes, I'll try that. Cleve, you should be able to talk now.
Hi, Sherry.
Hi, Cleve, how are you?
I always say this when the labs are measuring cost of doing business. It would be great if you could include some kind of measure of user experience in your costs. How easy is it to use the codes? How long does it take the user to solve a problem, not the machine?
Yes,
that's not in your
It is our responsibility, and also certainly it's our goal to have this very easy to use. So I mentioned this briefly here. The user responsibility is actually not very big, so you need to define this. And actually, I'm not sure whether I have a, I think I might have a, it's a, oops, sorry, sorry, I lost it, that's okay. It's a simple, so it's a simple Python code, the script to define this everything. It's not very much involved if you already have the function, and the most involved part is probably define this function, and then you develop an interface from this Python script to C or Fortran code. And then for all the applications I mentioned, we already have the script, so you can modify the script to do this.
Thanks.
Okay. Thank you, Sherry, for a very interesting use of Gaussian processes. So this concludes this week's ENLA seminar. But we have an exciting lineup for you for the rest of 2020. As you can see here, we have these 4 talks to go this year. Our next seminar talk is in 2 weeks' time on the 28th of October by Yuji Nakasukasa. Till then, we wish you a productive fortnight and look forward to seeing you again on the 28th. Bye-bye. Thanks, Sherry.
Thank you.